let's start. The lecture notes should be already on Canvas, and you can have a look there too. All right. So today I'm gonna teach you about how to multiply numbers faster than n squared. Like we all know, just from last lecture, that we can multiply two numbers of n bits in n square operation. Now we're gonna learn Karatsuba algorithm, which is faster. And by the way, if it's not multiplication, but you want to do addition or subtraction, two number of length n with n bits, can you say how much time do we need? Yep. Oh, n. Yeah. And what is like the algorithm that you know that can do it in n time?
You just do a digit-wise operation across them.
Pretty good. Yeah. Thanks. Yeah. So but like for addition and subtraction you can do fast. What about multiplication? How fast you can do? So right. Okay. So again, the problem is that you have two numbers a and b, each has n bits. You want to multiply them. That's the problem. Very simple. And the first algorithm in class that we're going to learn about is Karatsuba multiplication algorithm. This is an algorithm that is based on something called divide and conquer paradigm. So if one need to summarize what is this paradigm, then I would just say that it's a paradigm that you are given any problem, then you try to reduce this problem to the same problem but smaller size. Try to do recursion, basically. So this might be a bit abstract, but we will see how to do this in action. And my plan is just to show you first how to do divide and conquer, but at the end, you will get something that is as slow as n squared. But with just one more insight, then we will see that you can speed up n squared algorithm. So okay, let's start with like a slow divide and conquer algorithm. Okay, to multiply two numbers. All right, so we have a and b, and let's say that I just write down binary expansion of a and b into like numbers like this. Like a can be like 1 0 0 0 1 0 1 0 1 1, something like that. And this part is the most significant bit. This part is the least significant bit. Okay, I just write it down. They have length at most n. And then what I'm gonna define is just that I'm just gonna say that the first half here, the most significant half here, I call it a high. This is just a number of length n over 2, right? And then there is a low on this half, just another number of length at most n over 2. Well, do the same thing for b high and b low. Okay, that's the definition. And once you define a high, a low, b high, b low, then the way to write it down is that a can be written in this way when you want to write it with a high and a low. Make sense? Okay, do the same for b. Okay. Yep.
So a high has essentially, so when you multiply a high plus 2 to the n over 2, you're padding it out with zeros?
Exactly, exactly. Yeah, this thing is really just about shifting by 0. Yeah. Right. Okay. Okay, so I can write a and b like that. And now, just from the definition, you can see that if we want to multiply a and b, you can say that to multiply a and b, it's just about multiplying smaller number, a high, a low, b high, b low, in this way, right? Just expand this and multiply them and put it into this term. Okay, so to multiply n numbers, this can be done using 4 multiplication of n over 2 bit numbers, right? This is just one multiplication of n numbers, and how to do that? You just need to multiply this, and this. So that's like a 4 multiplication of n over 2 bit number. And then once you have, suppose that you have multiplied these have done with these 4 multiplications, what else do you need to do? Well, you just need to shift this thing by n times. This is easy because it's just really shifting numbers, right? And then do the shifting here a bit. This you don't need to do anything. And after you are done with that, you just add them up, right? But you know that adding is easy. All of this is just like a number of length, like of size at most n. So you add, you do constant many operation of adding. That takes you O(n) time as well. So just to conclude, to do one multiplication, all you need to do is to do 4 multiplication of smaller number, half size. And then once you have done that, just take some easy operation that can be done in O(n) time. Make sense? Okay. And that gives you this kind of recursive equation if you want to analyze the running time. So if you define t to be the upper bound of the time that you need to multiply to n bit numbers, well, to do that you just need, this is the time. How much time do you need to do that? You need to do like do 4 multiplication of number of length half the size, plus something that takes just linear time, right? And if n is 1, then that's just take constant time. And once you have this equation, well, you just need to solve this recursive equation and see what happened. But it will turn out that this recursive equation gives you n squared, which is as bad as the trivial algorithm. Okay, but let's see at least how do you do this? How do you solve this thing? There are many ways to solve recursive equation, but there will be like a bunch of this in homework that I want you to try to do it. But one way to do this recursive equation, to solve this, is just do it by expanding this into trees. So for example, at the top level is about n bits, right? And then for each of the problem, you expand the problem into 4 parts, right? For each of the part, now is the problem of size n over 2 bits. Okay. And do the same thing here, like for each of this guy, when you recurse here, you recurse it into 4 ways. Now the problem has size n over 4. Okay. So what's the depth of the tree? First of all, it's going to be just log n base 2, because every time that you have the new level, you have the size of your number. How many times you can do that? Just log n base 2. Okay. And now let's try to count the total work that you need to do on each level, right? So the total work on the first level is just O(n). And now, but how about the total work in the second level? And like let's say like for any level D. How do you do that? Well, the way to do that is just first, you need just to count how many subproblems are there in the D level. And that's going to be 4 to the D. Why? Because every time you branch out by like a factor of 4 for every level. So at level D, there's going to be 4 to the D subproblem, right? And for each of these subproblem, at level D, it's going to be the number of how many bits? Just n over 2 to the D bit, because you have the size for each of the level. So that's the total time that you're going to spend on level D. And this is, so when you multiply this, you get this. And now you just need to sum up overall level, sum the time that you spend on each level. Like first you spend like n, and then 2n, and so on. And this time is like basically the time that you spend on the last level is this, and that is just n squared. Okay. This thing dominates everything here. Okay. Question?
This algorithm works for any number base, right? All you would do is adjust the definition where you split it into the high and low, and you change that from like 2 to 10 or something.
Yeah, right. Good question too. Okay, so another way to solve the this recursive equation is just to use master theorem. You can look up what it is, but I guess some of you have heard about it. But now, okay, let's say like that's too bad. Like it is a divide and conquer algorithm, but it's as bad as trivial one. Now let's see how to do it better. So okay, recall that we have this equation. To multiply that one number, it involves 4 multiplication of smaller number. However, the key insight by Karatsuba says this. If you look at this term, this thing, you can just rewrite this in this way. Just rewrite this into this thing. Okay. So this is like the thing. This expression looks like something that involves just 2 multiplication, and you rewrite it into something that looks like it involves how many multiplication? 3. Like 1, 2, and then 3. Why this is true? You can just, multiply and like why this equation is true? You can just multiply and verify. There's nothing deep about it. But if you look at this, from 2, it gives you 3 multiplication. But what is good about this thing? Well, you see, this is just the same as this thing, and this is just the same as this. Which means what? If you already have computed this a high times b high, a low times b low, then you can reuse it here. And you just need one more multiplication between this and this to get this term. All right. And that basically just suggests us to, this suggests the different algorithm. This insight, the algorithm is just first, let's say you compute z high, which is just b high, a high times b high, and z low, which is a low times b low. And then you compute this c, which is this term. So that's just 3 multiplication of number which is of length n over 2, right? And now, just from this 3 multiplication is enough to give you a times b. Why? From c high, you get this term. From 0, you get this term. But to the term in the middle, right? You just reuse z high and z low, and minus it with c here. Why? Because just follow this equation here. This is just c high plus c low minus c. Okay. Does this algorithm make sense that it computes the correct result? But just from here, right, you see that from this equation, it means what? It means that now to compute one multiplication of long number, n-bit number, you just need to do 3 multiplication instead of 4 of short number, like n/2 number, n/2 bit numbers. And once you have done that, just do some addition, subtraction, or shift. And that total time is just O (n). And that basically, like, that's it. Like, that's the key insight. You reduce the number of sub-problems from 4 to 3. And that looks good. Just to make sure that you understand the algorithm, here is a pseudocode. Like, you can just write down the function to multiply A and B. If the number are short, just multiply them. You're done in constant time. Otherwise, just define A high, B high, A low, B high, B low. Compute Z high by recursively call the multiplication algorithm on A high and B. A high, B high. Compute 0 by recursion. Compute C by recursion. And just return this. That gives you now the new algorithm with running time that have a different recursive equation. That is, instead of 4 here, you get 3. Right? So now we just need to solve this recursive equation, and if you try to solve it, you get this thing, n to the log base 2 of 3. Well, again, you can use Schmeisser theorem, but there's always a way to just, like, you can always do this by hand and see what happened. I will not just go through this calculation. You can just try to follow yourself, like this at home or something. But I just really just expand things, do it again and again until the argument inside is 1, and that's when I stop. Once I expand everything, I just sum them up. I get some geometric series, and this term just dominate everything. Just get this, and I'm done. Okay. So how to do expansion and calculation, I let you do it, try to review this at home. But anyway, this is now into the 1.58 something, which is faster. Okay. All right. So how like, just to reflect upon this a bit, like, how did we get this improvement exactly? Well, we just reduce a big problem of size n to the same problem of smaller size, right? And if the number of sub-problem is is non-trivial, basically, instead of 4, you get number of sub-problem to be 3. Now you get some nice improvement. And like, just as a wish, if you want to think like a wishfully, what would it be if you manage to reduce the number of sub-problem to just 2 instead of 3 somehow? Well, like, this term in the recursive equation is going to be just 2 instead of 3. And if you try to solve it, you get n log n. Although this is not what Karatsuba achieved, right? But like, that's the hope. Like, what can we do something like that? And incidentally, this is not an accident actually, but the state of the art for integer multiplication right now takes actually n log n. But like, the algorithm, like, is based on the hope that actually you want to reduce the number of subproblems to 2. But the algorithm here is much more complicated. What I'm gonna do next is like to give you the flavor of how to get something like n log n, but for a different but related problem of polynomial multiplication. not integer multiplication. Okay, before I go to the next thing, from in polynomial multiplication, any question?
So with like them discovering an orthogonal algorithm, does that mean that processor companies are now going to try to rewrite their processor instructions to go and use that, or is there a way to do that?
I don't quite get the question. Say it in. Sorry.
How can you translate from like normal multiplication to Karatsuba's algorithm to this state-of-the-art algorithm in terms of like the processor on the computer?
Oh.
Is there an easy way to like design a processor that can use this process to do fast integer multiplication?
I'm not so sure. Like so Karatsuba algorithm is implementable and like a practical. This one that gives you n log n is not good actually, like in practice. But there is this algorithm that takes you like n log n log n that is discovered like some times ago, like 40 years ago. That actually is quite good. This is by Strassen and Schoenhager in 21, I guess. Okay. But that's a valid thing. Like, whenever you see any algorithm with like good asymptotic time, doesn't mean that it's implementable. Like, it really depends on like how complex it is, and so on. Anyway, next problem is polynomial multiplication. Before I define the problem, let me give you some toy problem that motivate this. So, by the way, like that's the technique that we're gonna learn how to do polynomial multiplication fast is fast Fourier transform. The thing that I mentioned in the first lecture that is very impactful. Okay, so a toy problem. Suppose that you have two sets of numbers, a set S and a set T. It just contains a bag of number. Okay, and suppose that you want to know how many ways you can pick one number in S and one number in T, so that they add up to some fixed number that you want. Let's say 25. Well, in this, a way to write it down mathematically is just like this. You ask a pair of S and T such that the sum of them is 25. By the way, from this example, you see it's like there are three ways. This, and this is there. Three ways. Okay. But like you can ask this in general. If you have a set S and set T, each has length n. Like there are n numbers in there. You ask like, can you sum it up to, let's say, 10? Like how many ways to do that? Well, I have a question for you. Suppose that number in S is sorted, numbers in T are sorted too, and I give you one fixed number like 25. Can you give me maybe like a way to count how many ways you can pair this up in O of n time? Any suggestion how to do that? Yep.
You could put all the numbers from S into like a hash table, and then you can go through the numbers in T and C and check whether the corresponding like complement of that number that adds up to 25 is part of the hash table.
Yeah, right. Yeah. But good. There might be a way that you don't even need hash table.
Yeah. You do a double pointer, like one point at the start, one point at the end, and you just move.
Yeah, good. Yeah, that's like a simple way to think about this. Kind of just start from pointer on the beginning of S, pointer on the end of T, and try to, that any pairs that gonna add up to some fixed number is gonna like go in this direction, and you kind of do it. You know what to do, like okay. Or do it as an exercise. Anyway, you can do it for one number. You can do it in O(n) time. But what if I asked you a harder question? That is, instead of fix one number like 25, I actually want you like to do this for every number I. Like for every I want you to count how many ways you can pair up numbers so that you get the sum of I. Okay. For one fixed I, you can spend O(n) time. But what if I want to do this for all I simultaneously? Okay, that's the question. And let's say that, suppose that I is like ranging from 1 to n. Then a trivial way to do this is like n squared time, because for each I you spend n time. Now, with polynomial multiplication, you can do it faster. I'm gonna teach you how to do this polynomial multiplication in like n log n time. And you will see that from polynomial multiplication, you can use to answer this for all I simultaneously. So you get very good improvement. Okay, why this problem is related to polynomial multiplication at all? Okay, that's not too hard. Let me try to define two polynomial ax and bx. And then, like anything that is in the set S, I just put like a x to the 9. Like I just create like a x to the 9 plus x to the 10 plus x to the 11 plus x to the this. That's one polynomial. You can define it. And do the same for B. For set T, you create a polynomial B. Do the same thing. Okay. And you just multiply these two polynomial. Okay. Let C be the multiplication of A and B as a polynomial. Okay. Now, C is a polynomial, so you can set, like I can just set it, let's say that Ci is the ith coefficient of Cx. That is, I can write Ci in this way. Now you can realize, if you just think about it a bit, you will see that Ci is just exactly like a number of ways you can pair up S number in the set S and set T so that it adds up to I. Okay. Good. So basically, it means what? It means that the result of polynomial multiplication, which is C, really just encode for every I how many ways you can like pair up numbers so that they add up to I. You get it in one go for all I. Okay. So there are many more applications of polynomial multiplication, and you'll see this in the homework too. All right. Now, so that's just why polynomial multiplication might be useful. Now let's define the problem precisely and try to solve it. So the problem is that you're given two polynomial, and this polynomial, like you are given the list of coefficient of polynomial. I'm given list of number a0 up to an minus 1, which is just the coefficient of ax, and I'm given another coefficient list of polynomial bx. That's my input. And then what I want to do is to compute the the multiplication of this polynomial. And what do I mean by I want to compute this? I want the list of Ci, the coefficient of C. Okay, so that's the input and output. List of coefficient for A and B, and I want the list of coefficient for C. So if this has n number, this has n number, well, the coefficient of C is going to be the list of something like 2n, right? Because now the degree of polynomial increased from n to 2n. Okay. And you observe that Ci is nothing but this thing, summing over all j ranging from 0 to I, aj times bi minus j. So that's why like this exercise, like that's why you get this exercise basically, just from the definition of how you multiply to polynomial. And by the way, polynomial multiplication have another different name. The problem of given A, list of A and list of B, and computing C, which is defined like this, is also called convolution. If you want to look at the internet, like that's a word. So convolution and polynomial multiplication are the same problem basically. Okay. Anyway, just from the definition of Ci, right? You can see that you can compute Ci using On at most arithmetic operation, because it's just a sum, like a sum of at most n term. And there are n many of Ci that you need to compute. So trivially, you can do it in n square operation. That's a trivial way to compute polynomial multiplication. But what we're going to show is that you can do it in O n log n. Question about the problem? All right. And now there is a catch though. When I said that I can do it in O n log n arithmetic operation, what I do is that I'm just gonna count how many subtraction, addition, multiplication between numbers are there. Actually, it's gonna be even complex number. So I kind of omit like a way how to implement this in real computer, because how do you even represent complex number in real computer? And like maybe when I add things between two numbers, these two numbers might be large, but I just count it as one operation. Okay. But here, what I want to do is to convey you how fast Fourier transform works. I want to give you that idea. So I'm just gonna ignore this stuff and just count the number of arithmetic operations. Okay. All right. So okay, before we start with the algorithm, I need one background on algebra. Okay. So you can, like, given any polynomial, you can represent it in different ways. There are at least two ways to do that. One way is just to list all the coefficients of A, like this. Just list all the coefficients. Like that is still given AI. This is like a way that we give like the input of that we have basically. This is a way to represent A. Well, there are another way to represent A. That is just to use point value representation. What do I mean by that? Well, I mean that it's like a pair of points. I'm given like a point, let's say 10, and then I evaluate A at 10. Like just put 10 into this polynomial and evaluate it, right? That is, let's say ax is the x squared plus 1, then a10 is just this plus this, which is this. Yeah. So this is just one evaluation point. And I said that I'm just gonna have this n many evaluation points ranging from, like I have point pi ranging from I equals to 0 to n minus 1. I just evaluate it at n points. Now, there is the fact from algebra that I will need in this class. That is, actually, if you have any polynomial which degree that is small degree is at most n minus 1. Okay. Then, if you fix any set of points, n of them, and evaluate this point at this a, then this point will determine what a exactly is. Another way to put this is that suppose that you have some guys that like any polynomial, two of them, a and a prime, and let's say that you have excess in a black box where you can only evaluate them. You don't know anything else. Okay? If it turns out that, but you have a promise that they have small degree at most n, but at most n minus 1. But if you suppose somehow that they are like if these two things you evaluate them and they agree at least n many points, then you know for sure that they actually must be exactly the same polynomial. That is, if you write it down as a coefficient list, you will get exactly the same coefficient. Okay. So is the statement of this fact clear? I don't need, yeah.
So basically by this, if you had x squared plus x, like anything with x squared, you need 3 points and you can only have one quadratic.
Yeah.
Okay.
Yeah. Right. Exactly. If the degree is is 2, then you just need at most 3 points to determine what exactly is that polynomial. Why this is true? Well, that's I will not prove it, but I will need this fact in the class. So you should know, at least understand this fact, like the statement. Okay. Question about this? Good. Okay. So now, one good insight is this. Suppose that instead of, let's say that my problem is still polynomial multiplication, but instead of having an input as like a coefficient list, I'm giving like the input that is given to us is like the point value representation. Okay, I changed the representation of the input to point value representation. Now I claim that this problem of polynomial multiplication now become much more easier. Why is that? Well, suppose that you have point, you have evaluation point at pi of a and b. What is the evaluation point of c at pi? Well, it's gonna be just, yeah.
API times BPI.
Very good. Yeah, API times BPI. Yeah, and this is something that you are given, so you can just multiply them together, right? So all you need to do is just multiply the input point-wise, and you're done. Okay, but one thing is that what you will need, how many points that you need, is going to be something like 2n, not n, because c now have degree like 2n, so you need at least 2n points to determine c. Okay. So if somehow I can get the evaluation point to n many of them of a and b, now I can just compute c like a evaluation point of C very fast in ON operation, just 2n operation really. Okay. So the plan with this, then our plan is the following. I will basically just reduce the problem from polynomial multiplication to polynomial evaluation. That is, what we are given a coefficient of A and B. We want a coefficient of C. What we're gonna do? I'm just gonna choose some point and evaluate them, evaluate A and B at many points. And then once I have that, I can just get a point value, a representation of C very quickly, right? Just multiply them pointwise in ON time. And that's just represents C, but it's not a representation that we want, so we need to convert it back to coefficient representation of C. So that's the plan. We know that at least one step is easy. How do you do this step and this step? That's the question. So what I mean is that now all we need to do is to design some special set of points to n of them, such that you can evaluate all of them simultaneously very fast on A and B. You want like this evaluation point, evaluate them at A and B super fast in just n log n time. And once you have that, you're just gonna get evaluation point of this set on C. And you want to convert it back to the representation, the coefficient representation of C. And we need to do the first step here is just this, which is we need it to be n log n. And the second step is this part, which is we want it to be n log n as well. Okay. So that's the plan. If we can do this, you agree, we are done. Okay. So now, how come that this set exists? Well, like you see, like if suppose that you want to evaluate A at one point, how does it look? How does A look like? A is a sum of like n many terms. So just to evaluate one point, it seems like you need n operation already because it is a sum of n many terms. Now I want to design like n many points so that you can evaluate all of them simultaneously in just n log n time. So how come that's possible? Well, it is, and you will see soon. Okay. So this set of points actually exists. Okay. And you see, like now I said that like I need like to evaluate 2n many of points, but just to make the problem easy to state, so that my explanation is easier to look at. Let's say that I instead of designing a point, the set of point with like a 2n minus 1 point, let's change the parameter a bit, and let's say that I just want to come up with n many points, and also below I might be sloppy a bit, like sometimes the degree is n minus 1, I might just say the degree is n, because I don't want to just be cumbersome with this plus 1 minus 1 thing. So the goal was the goal again. The goal is just to choose n points so that you can evaluate all of them fast in just n log n time. Now, we will not go to the final solution yet, but let me tell you some motivating example. If I define, let's say A is just like this polynomial, I can define A even and A odd. That is, I just collect all the coefficient, all the even coefficient here, and put like and write down the polynomial that have all even coefficient of A, and do the same for A odd. A odd collect all the odd coefficient. So A even and A odd has degree, which is now n over 2 instead of n. It has smaller size. So we do this because we want to do divide and conquer. We need to define somehow smaller problem. Okay. Now what's good about A even and A odd? Like you see that AX can be written as A even and A odd like this, right? Just put A even but evaluate it at x squared and do the same for A odd and then times x here. Now, that's just from the definition. But what is nice about this? Well, if you look at, suppose that you want to evaluate A minus x, okay? Well, then like you need to evaluate A even at x minus square. But that's just the same as x squared. So now what's good about these two things? Well, now you see that this looks like something that we can reuse. Once you have compute this thing, by recursing on this and this, to compute evaluation point at minus x, you can just reuse this too. You don't need to redo it. Okay, so again, like this is like basically the idea of how come like there is a saving in number of subproblem. Instead of 4 things, you just need to do it only 2 things and you reuse 2 of them here. Okay. This is, you see, like this is kind of similar to when you do integer multiplication. When you have 4 subproblem, you reduce it to 3. Here, from 4 subproblem, I kind of reduce it to 2. But okay. Anyway, right now you just need to observe that it seems like now you can reuse stuff. Now, more formally, suppose that I want to choose endpoint like this. My point set is like a pair of points, like a P1 and minus P1, P2 and minus P2, and do this in pairs. Okay. And you see, all I need to do to evaluate this at n many points, well, I just need to evaluate them at A even and A odd, but do it at this thing square. But when you square them, then like these things are the same number, these things are the same number. So actually you get this set. This set now has size n over 2. Although this set has size n. Okay. So there are just to evaluate A at n many points, you just need to evaluate A at A even and A odd at n over 2 many points. And once you have compute that, like a once you have evaluate A even and A odd at all these points, all you need to do is just like for each point you just need to like do some constant number of operation, multiply like some pi to this and some addition. So for each point you do constant number of operation to get like the evaluation point of A at both P and minus P. So what do we get so far? We get that to evaluate degree n polynomial at n many points, I just need to look at 2 polynomials, which is A even and A odd. These 2 polynomials have degree now half. And I also need to evaluate them at n over 2 many points, half again. So this is basically the same problem as before, but half the size half. Okay. Once I have done this, you just need to spend n additional operation, just for each point I spend like a constant many operation here, right? So there are n many points, so I just spend n additional operation. So what does it look like now? It looks like we get a recursive algorithm such that we have a problem of size n. You reduce problem to two subproblems on A even and A odd of size n over 2. Once you have done that, you just do n operation more. Okay. And that, if you solve it, you're just gonna get n log n. So that looks good, except that there is a bug. Like there is a problem with this argument. So the problem is that this set of points that you want to evaluate on A even and A odd, they are all positive number, right? But like to be able to get this trick done, you actually need that the set S need to have like a pair of negative number, like a pair of positive and negative number. So it means what? It means that you cannot really continue this strategy from on the next level. The recursion algorithm actually doesn't work. So, question up to this point? Like you see, like there is a problem with this. Okay. So now let me tell you but like we have the right idea actually. So to make this idea works, we will actually go to complex number. So what I'm gonna do is that I'm gonna like choose my point set of n point is just gonna be all the root of unity. What is, just to remind you what is root of unity, omega sub n is just a solution of x to the n equal 1. Okay. So, for example, was omega 2 like, so what is like what's the solution to x squared equals 1? There are two solutions, which is 1 and minus 1. For x to the 4th equal 1, there are like 1, I, minus 1 and minus I. So basically omega 4 is just I. And then you can write all this in like the power of omega, right? Omega 4 to the 0 is just 1. This is I. And I squared is minus 1. And I to the I cubed is minus I. So in general, what do we have is just this. Omega n is just like when you kind of rotate in this unit circle of the complex plane, right? Omega n is here, omega n squared is here, and so on. And omega n to the n over 2 is like you walk half the way. So this is just minus 1 here. This is 1. This is 0. So this is omega n to the n over 4 is just you have quarter of the way. So this is I. This is minus I. Anyway, this is just what is root of unity. Okay. And that's gonna be some like wait, I have a block. This should be x. Just ignore this thing. Ax is a even x squared plus a odd x odd. Okay. So now there are like some property of root of unity that you can just let's say that let's go through them quickly. Well, like the nth root of unity square is just the n/2 root of unity, right? So this thing square, omega n square is just omega n/2, right? Because you see, like I'm not sure how much algebra you like. Does this make sense to you? Like, okay, good. Anyway, like it's just some basic algebra that you can just verify yourself. That's not the point of the algorithm. The point of the algorithm is that, let's see, you know that AX can be written as A even and A odd in this way, which means that if you want to evaluate A at all, like at the root of unity, right? For all of them, which is omega to the k for all when k range from 0 to n-1. If you want to evaluate this, just use this equation, you get this thing. Right now, I didn't do anything. I just put omega n to the k to this equation. Nothing happened. And now this is when I use the property of root of unity to derive the following. We would have that for every k that you range from 0 to n/2, when instead of like this thing, I can just rewrite it in this way. This thing, that is, instead of omega n to the 2k, this is now omega sub n/2 to the k. Okay, and I just write down it here. So, okay. From here to here, this is just algebra. But you can verify this. But the point is that now if you look at this, it means what? So you can try to verify this at home or something. But let's interpret this equation. What you have from here is that if you range from if you range from k from 0 to n/2, and you evaluate this thing and this thing, you would have the evaluation of A at all root of unity, right? This is like a first half of root of unity. This is the second half of the root of unity. So if you evaluate all of them, you're done. But now, suppose that you have what do you need to do to evaluate this at the nth root of unity? You just need to look at A even and A odd, which have degree n/2. And now what is the point of evaluation of A even? You just need to evaluate it at n/2 now. n/2 root of unity, not n root of unity. n/2 root of unity to some power. Okay. Do it the same at A odd. And how many points that you need to do on this A even and A odd? So basically, you just need to evaluate A even and A odd at all n/2 root of unity. Once you have done all this, it's just like for each point, you just spend constantly many operations to get this thing, which means what? It means that you just spend like an O(n) operation in addition after you have done with the recursion. So let me try to to summarize what we get from the equation above. What we get is that to evaluate A, which is the degree n, at all nth root of unity, just need to look at two polynomial A even and A odd, which have degree n over 2. And now you evaluate them at all n over 2 root of unity. So that's really the same problem, and the size of the problem is now half. Once you have done that, you just spend O(n) time. Okay. So you see that now there is no problem because the structure of evaluation point is really the same like from before. Like from the structure of evaluation point is like O(n). Now you just want to do it at n over 2. Like for the structure of evaluation point used to be all n root of unity. Now you just do it at all n over 2 root of unity. Good. So that's why it's a valid divide and conquer algorithm. And when you analyze the running time, this is just the equation that you get, right? You have the t be the time that you need to do, like a problem on the problem of size n, that is evaluating degree n polynomial at all n root of unity. Well, this now can be written as recurse on the problem of size n over 2, do it 2 times, and spend n additional time. And that gives you n log n if you solve this equation. So what do we get so far? We get that this step is done. You can evaluate A and B at so many points, n many of them, in just n log n time, if you choose the point carefully. Okay, so this is what is meant by fast Fourier transform, basically. Okay, so we are remaining, like we are not done yet because we need to do the last step here. So before going there, let me kind of, and by the way, if you want to understand, like just to make sure you understand, you can go through the pseudocode here. But I will skip that, and let's try to look at what we have done in just another way. That is, I want to view what we have done like as some matrix operation. Okay. So just from the definition that like to evaluate A at this point is just this sum. It means what? It means that all the points that we evaluate, like all the root of unity that we have evaluated, if you list all of them in vector here, I claim that this thing can be written as like a sum matrix vector product between two, sum matrix and vector. What is this matrix and vector? Well, the vector here is just the coefficient of A. And what is this matrix? It's just a matrix such that at the jth row, at the ith row and jth column, I put omega n to the I times j. Okay. So that is the first row and first column is like a to the 0. So this is all 1, and you see the pattern. And you see, like, let's try to verify one thing, right? If you multiply the last row to this column, what do you get? Well, you just get this sum, like a sum of AI of omega n to the n-1 to the I, ranging for all I. But that is just exactly this thing, just from the definition of polynomial. So now you see that like this, from this vector A to compute what we want, it's really just like another way to describe this is like to multiply 8 with this matrix. Let's call this matrix H. Okay, so now let's say that I define given polynomial A, B, and C, we can say that like let A vector of A, B, and C here be like the coefficient vector that describe the polynomial. And the vector YA, YB, YC is like the evaluation point of A at all root of unity. Basically, this thing is A, this thing is YA. Okay. This is just definition. Now you can see that if you multiply A, vector A to H, then it will just give you YA. Okay. So that is multiplying, like computing H times A is just the same thing as evaluating A at all root of unity. And you know that you can do this in n log n time. Like multiplying some vector to matrix trivially would take you n squared time. But you already know that if the matrix have this special structure, you have the algorithm to do that in n log n time. Okay. Good. So let me just try to like rephrase what we have done so far in the matrix view. So our overall goal is that we first are given a coefficient of A and B. That is, we are given vector A and B. Okay. Then what we do, we will just evaluate A and B at many points at root of unity. So what do? We just multiply it to H. Right? And then you get like this vector B, vector YA and YB. You can do this in n log n time. Once you have done that, you just need to multiply these two vectors pointwise. And then you will get the point value representation of C. This is point value representation of C. This is, we get y of C up to this point. And now all we want to do is just to convert yc to vector C here. This is this step. That is, we want to find a vector C such that if I multiply C to vector C to H, I would get YC. Another way to put this is just I want to compute C, which is H inverse times YC. Okay. So right now, we don't know how to do this yet. Like these two steps, we are done. But we don't know how to do the last step yet because how does H inverse look like? How to multiply some vector to H inverse and fast, right? That is not clear. But up to this point, like what I want you to get up to speed is that you should agree that like up to this point, all we need to do is just to know how to multiply some vector to H inverse fast. If you are done with this, you are done. That is, we're gonna complete the last step. Yeah. Okay. So now, how does H inverse look like? And how do we compute the matrix vector multiplication to H inverse? Okay, so what I claim is that H inverse, you can actually write it down in a super clear way, super concretely. H inverse actually just look like this. That is, it's really just some matrix such that the row and column, the ith row and jth column look like omega n inverse times I and j. So what is omega n? What is omega n inverse? Well, it's really just like it's just this thing, right? Omega n is going this way. Omega n inverse is just this guy. It's basically like omega n, but going in the clockwise instead of counterclockwise. Yeah. Okay. So if now you see that like this is like omega n inverse, and like on each point you just on each row and column you just put like a I and j here, like a 2 in the power. You see that this is really like you see this looks like h exactly. In h, it used to be that in point I and j, you put omega n to the I times j. Here you put omega n inverse to the I times j. So it's really like the same matrix, except that you go counterclockwise or clockwise. You put like omega n or omega n inverse. Just put like a omega n inverse to the in place of omega n, and then at the end scale it down by 1 over n. So that's just the claim. That's how H inverse look like. Why this claim is true? Well, like we can just verify that H times H inverse is exactly identity matrix. And if that is the case, it must mean that what I just described here is exactly the inverse of H. If they multiply together and you get in identity, then you must be done. It must be an inverse. And how do you say this? Well, this is now just do some math. You can verify this. I won't go through this. But what do we get from here? Like you can just verify this at home. But what do you get from here? Is that to compute like to multiply some vector to H inverse, right? This can be done really exactly the same as like in FFT. This is the same algorithm because you just instead of defining your root of unity to be like the one that go counterclockwise, just define it to be the one that go clockwise. Just do that, and at the end, scale down by 1 over n, just because there is 1 over n here in the definition. So the algorithm would be just use the same algorithm. Like if you want to compute H inverse, like there are like some vector of y here, you want to compute like the coefficient vector, just do the same, really the same algorithm of like FFT, except that you replace omega n by omega n inverse, and then scale everything down by 1 over n. And that's why like it's just the same algorithm, except you change some parameter, and that takes n log n times as well. And that basically completes the last step, because you use it's the same running time here and here. Okay, so let me recap. What we have done so far is that to multiply two polynomials, what we like how did we do this? We instead reduce the problem to polynomial evaluation at n many points. Actually, to n many points. And to design a point set so that you can like and what the fast algorithm that we design is the algorithm for evaluating many points fast, and the point set that allows you to evaluate very fast is the root of unity. Okay. So by choosing the point set to be like a root of unity, it allows you to like basically it allows you to get this kind of recursion, that is, you have a problem of size n, just reduce the problem to problem of size n over 2, but repeat it just 2 times. And then spend O(n) additional time, and that's why you get n log n time at the end. Okay. So that's it actually. Question about this?
I'm assuming other practical uses of the roots of unity, in which case, where should we go to learn more?
Yeah, good, very good. So exactly what I put here. So I like if you want to learn more how to like avoid like using complex number, these are the good lecture notes to look at. Yeah, it's now like, so you can look at it. The way to do that is now more about algebra now, not about like how to design divide and conquer algorithm. So that's why I just stay at this level to convey you how to design divide and conquer algorithm. Yeah, but you can look at this certainly. More questions? Yeah.
So in the, I guess, first section, you were deriving the big O by like expanding it out and then conclusion. So then could you also use the master theorem, or is it expected in the class that you do that derivation?
Oh, you can use master theorem. You can like, I allow you to cite anything in the homework.
Okay.
Yeah. Yeah. As long as like it's a well-known theorem or something.
Okay.
Yeah. More questions before we stop? All right then. Thanks. See you next time.
If I can understand it, maybe that's